Welcome to lecture 16. The goal of this lecture is to classify valuation rings containing Z and FPT. So the goal is to classify valuation rings containing Z and FPT. So we'll start with a small lemma. Suppose you have a PID and you take a prime ideal then the localization is a discrete valuation ring. Which we call DVR. And so what's the proof? Well, every ideal in RP is obtained by localizing an ideal I of R. That is, if J is an ideal in RP, then this ideal J is just given by the localization of P, so it's of the form X over S with X belonging to I and the denominator belonging to R minus P. So in particular, if alpha generates I, let's call it the R ideal I, then alpha also generates the localization RP ideal J. And so in particular, if you localize a PID, RP is also a PID, and since we are localizing with respect to a prime ideal, RP is a local ring with maximal ideal. It has a unique maximal ideal given by the localization of P. Okay. In short, RP is a PID with unique maximal ideal and by proposition 38, which was characterizing DVRs, we have that RP is a DVR. Okay. So this completes the proof of the lemma that if you have a PID and if you localize it with respect to a prime ideal, then you get a discrete valuation ring. This completes the proof of the lemma. And now I'm trying to search for some sort of converse. That's the next proposition. So suppose you have a PID with fraction field K, And suppose you have a valuation ring of K containing R. Then this valuation ring must be of the form that we just discussed in the previous lemma. It must be a localization of R with respect to a prime ideal. Okay, so what's the proof? So firstly, V is a valuation ring. Since V is a valuation ring, V is a local ring with, say, maximal ideal M. And since it's a valuation ring, we have this corresponding valuation on it. And so what do we have? So we can write V as OKV, which is the set of all elements in K cross, such that the valuation of X is larger than equal to the additive identity along with the 0 element of V or R, and the maximal ideal is the set of elements in OKV with either X being 0 or its valuation being strictly larger than the additive element. Okay, and what we are given is that this PID sits inside this valuation ring V. Okay, now this is maximal ideal inside the valuation ring. Now if I take the intersection of the ring R and the maximal ideal, I claim that this intersection is a prime ideal. And so we've already seen some versions of this proof, of this claim. So I is a prime ideal of R, again Y. So if you take two elements in R with the property that its product belongs to I, well, the product belongs to I and I sits inside M. And since M is a maximal ideal in V, it is also a prime ideal. In V. So you have this product X times Y belonging to the maximal ideal of V. So this implies that either X belongs to the maximal ideal or Y belongs to the maximal ideal. But it also belongs, X and Y both belong to R, so X belongs to the intersection of M intersect R, or Y belongs to the intersection of M with R. That is, X belongs to I or Y belongs to I. Okay, so this proves claim A. So this intersection of R and this maximal ideal of the valuation ring is in fact a prime ideal of R. And just to emphasize, instead of writing I, I'll just call it P, which is the intersection of the maximal ideal and R. My next claim is that if I take an element in R that's not in P, then its valuation is in fact 0. Again, why? Now firstly, since alpha belongs to R minus P, it belongs to R, but R sits inside V, and every element of the valuation ring has a property that its valuation is larger than equal to the additive element. Now if the valuation of alpha was strictly larger than 0, what does that mean? It must belong to the maximal ideal, because that's how the maximal ideal of the valuation ring is characterized. It consists of all elements whose valuation is strictly larger than the additive element 0 gamma. But alpha belongs to M, but alpha is an element of R, so it belongs to the intersection M intersect R, but that's nothing but P. But by the hypothesis, alpha is an element of R that's not in P. So this leads to a contradiction. If we assume that the valuation of alpha is strictly larger than the additive element of gamma, so the only possibility, since the valuation of alpha is strictly larger than or larger than equal to 0, this additive element of gamma, and we've just shown that it can't be strictly larger than the additive element of gamma, the only possibility is that the valuation of alpha equals the additive element of gamma. Okay, so this proves the claim. Claim B. And what's our next claim? So I can take R, I know that R sits inside V by hypothesis. Now I want to localize it with respect to P, and my claim is that that sits inside V. And this inclusion is such that the maximal ideal of the localization Rp, which is the localization of P, sits inside M. Again, why? Now every element of Rp is of the form x over S, where the numerator belongs to R and the denominator belongs to R minus P. And similarly, you can write every element of its maximal ideal, PRP, is also of the form x over S, where now the numerator belongs to the prime ideal and the denominator belongs to R minus P. Okay. Now consider, so you take an element of the localization, let's call it x over S, and just observe that x equals x over S times S. And by using properties of valuations, so thus we have that the valuation of x equals the valuation of x over S plus the valuation of S. Okay, and now since little s belongs to R minus P, by the previous claim, its valuation is in fact the additive element of gamma, and so this means that the valuation of x equals the valuation of x over S. And so if x belongs to R, then we have that the valuation of x over S is the valuation of x, which is larger than or equal to the additive element of gamma, and so this means that x over S also belongs to V. And so this shows that the localization Rp sits inside V, and if x belongs to the prime ideal, then we have that the valuation of x over S again is the valuation of x, but if x belongs to the prime ideal sits inside the maximal ideal of the valuation, and every element of the maximal ideal has valuation that's strictly positive. And so this shows that under the above embedding, that the maximal ideal of the localization Rp sits inside the maximal ideal of M, because every element of PRP has valuation that's strictly positive or strictly larger than the additive element of gamma. Okay. And so in other words, what we've shown that V dominates Rp. Okay, so let's keep this fact in mind, that V dominates Rp. Now, what are the facts that we know about the prime ideals of a PID? So either, so if since it's a domain, 0 is a prime ideal of the PID, and the other fact is that if you have a non-zero prime ideal, these are maximal, generated by pi for some irreducible element pi of R. Okay, and anyway, so the first case is that if P is just 0, then the localization is with respect to the 0 ideal, but that just gives you the fraction field K itself. And so in this case, we have that K is Rp, sits inside V, but V sits inside K. So this just means that Rp is K in this case. And so we are done. And case 2 is if P is not 0, then P is generated by some irreducible element but in this case as well, Rp is a DVR by this previous lemma, lemma 39. In particular, Rp is a valuation ring, but if you're a valuation ring, your maximal in the domination inside the fraction field K. Again, this was summarized in theorem 35, lecture 13. And since we have that Rp sits inside V with V dominating Rp, this is only possible because of this maximal property that Rp should equal V. Okay, so in either case, this valuation ring containing a PID R is of the form R localized at the prime ideal of the PID. So this completes the proof of the proposition. Now to use this proposition for the integers, so corollary, every valuation subring of Q is equal to Q or Z localized at P for some prime ideal prime number P. Okay, so proof, again let V be a valuation ring of Q for some valuation, say V on Q cross. Now we've seen that, I think this was lecture 9, lemma 22, that the valuation of 1 should be the additive element of gamma. So in particular, if you have a valuation ring, 1 must belong to it, and thus the smallest ring generated by 1 must belong to V. But what is the smallest ring generated by 1? That's just Z. Inside Q equals Z, and thus we have that Z sits inside V, and since Z is a PID, you just apply the previous proposition, this proposition 40. So we have that this valuation ring is the localization of Z for some prime ideal, capital P of Z. But since Z is a PID, every prime ideal is either the zero ideal or is generated by an irreducible element, but every irreducible element in Z is up to a unit given by a prime number, and so thus V is given by the localization of the zero ideal or the localization at some irreducible element, but these are all prime numbers up to plus or minus 1. Okay, so this completes the proof of the corollary. So we've classified all the valuation rings inside Q. They must contain Z. Z's a PID, and so using the previous proposition, what we've seen is that every valuation ring in Q must be the localization of Z with respect to some prime ideal. Now we can similarly play the same game. Suppose you consider the field Fp brackets T, again with P prime, and let V be a valuation ring inside Fp brackets T. Now again, since V is a valuation ring, it's a V ring. So this indeterminate T is not 0, so either T belongs to V or 1 over T belongs to V. So just to avoid this ambiguity, you can choose the indeterminate to be either T or to be 1 over T. So choose the indeterminate U equals T if T belongs to V, or choose the indeterminate to be 1 over T if 1 over T belongs to V. Okay. So what do we have? Again, 1 belongs to V, which implies the smallest subring generated by 1 inside Fpt lies inside V. This is because V itself is a ring. But what's in characteristic P, what is the smallest ring generated by 1 is just Fp. We've just chosen the indeterminate U so that U belongs to V. So Fp belongs to V and U belongs to V. Thus, and since V is a ring, the smallest ring generated by 1 and Fp lies inside V. U and Fp lies inside V. So what's the smallest ring generated by U and Fp? It's the polynomial ring. So Fp brackets U, the polynomial ring, sits inside V. And again, since Fpu is a PID, applying proposition 40 again gives you a similar result. For this function field, we have that every evaluation ring of Fq brackets T is of the form, well, it must be the fraction field is Fpu localized at the 0 ideal, or Fpu localized at some prime ideal generated by an irreducible element. Let's call it f of u, where f of u is an irreducible polynomial in this one variable ring Fpu. So the localization with respect to the 0 ideal gives you the fraction field. That's just Fp round brackets u, which is nothing but Fp round brackets t, or is Fp u localized at f of u. Okay, so this completes the characterizations of valuation rings inside Q and Fp brackets T. Okay. Thank you.